start. So, yeah, I wanted to start this project about the Kaggle competition because I think they're really useful to learn how to manage a real case, a real project. And so even if you don't have that much of experience, there is a lot of resources online, and Kaggle also is a very good platform to learn. So there are competition, fairly basic, so that you can start, and a lot of people wrote about that, and a lot of examples. And so even if you don't have a lot of experience, it's still useful and also fun to do. And so what I wanted to do today is to have everyone to arrive at a basic level, basic understanding of what a Kaggle competition is and how a machine learning project is structured, and also with some examples. I will do some coding with an example and an application to a competition. So just for starting, who of you is from the bachelor? Okay, quite a lot. Who of you has done some machine learning courses here at Politecnico from the master? Okay, who has already participated to a Kaggle competition? Okay. Yeah, so today I will be, also because we don't have a lot of time, I will go mainly about the concept and the abstract level, more with respect to the details, because we don't have so much time. So, since many of you have never used or worked on a machine learning project, oh, by the way, this is not a lecture, I'm a master student, I'm at your age basically. So whenever you want, interrupt me, you don't even need to raise your hand, just interrupt me, I'm not a professor. So, when you work on a machine learning project, you will have to deal with a lot of libraries, like these ones: NumPy, SciPy, Pandas, scikit-learn. But don't be scared, because there's a lot of documentation. They're all well integrated with each other. So I think you will not need to follow a lot of tutorials and courses and buy books on that. You can just learn on working with that while you're working on the project or the competition. Whenever you need to do something and you don't know how, there will be me or us or whoever will be in these meetings, or you can just search on internet. There is a lot of documentation. So basically, you have NumPy, SciPy for linear algebra, multiplication of matrices and stuff like that. Pandas is a library for handling data frames, which are tables, which is actually your data. And scikit-learn is a very good library used everywhere for machine learning, from the simple stuff like linear regression to a lot of other models. Then matplotlib and seaborn to plot. You will have to plot a lot. And Jupyter Notebooks is the software library that you can use to work directly, and is very useful for visualization. So for some of you, I would say some obvious things, but I wanted to have everyone at basic level. So when you're working on a machine learning project or a competition, you usually have a data set. For example, we will see the house prices data set, which is a challenge from it's a challenge that is one of the challenges that I use for learning. So it never stops. While usually some like the official ones are have like a limit of 3-4 months, and then you have the challenge finishes. So it goes forever, and I will use that as an example for whatever I will do. And you basically start with a data set made by samples, which are the rows. In this case, each sample is a house, and then you have some columns, which are called usually features, which are the characteristics of the sample. So, for example, here you have the area of the lot, you have the neighborhood, or you have the style of the house, and the kind of streets it has and stuff like that. And usually inside some features you have some missing values, which could be an error on when someone puts the value in the data, or there be a reason for that missing value, and I will explain how to handle them. And usually the setting is the following. You have a data set with the training set, which is the one that you will use for learning, and then you will have to learn for example, this, you can't see well, but this is the price of the house. So basically, based on the features of the house, you have to predict their selling price. And you have also a test set. So are other houses which are not in the training set with the relative sale price. The problem is that you don't have the target. You don't have the test set, the target for the test set, and so you will have to predict it. And based on how well you predict the target set, you will have a score. And we will see how it's computed. There are usually two kinds of problems in machine learning, which are regression and classification. Our problem, the house prices, is a regression problem because you have to predict a numeric value, like 200, 8,000, and so on. But then there is another competition, which is a classification problem. Also, the Titanic is a competition hosted to learn, in which you have to predict for each passenger of the Titanic, based on their characteristics, if they survived or not. So you have two labels, yes or no is not a numeric value. And you can also have multi-class classification. For example, if you have to suggest, like predict a product that would have been bought by a customer, you have like 3-4 different products, and you have to predict which one of them the customer will buy. This is also a classification. It's not a numeric value, but with more than two classes. It's not binary. So the typical workflow of a challenge is the following, which is part of what is usually for a machine learning project. And you have there are some courses here at Politecnico that covers a part of them. One is text mining, which is data mining and text mining, which is kind of broad and goes briefly to a lot of steps of the typical workflow. Then you have a lot of courses that are more on the bottom part, which is the one that you do more research on. For example, for the kind of model that you can use and how they work, artificial neural network and machine learning, and also recommender system for building the models and validating it. So starting from the exploratory data analysis, this is a really, really important step because it helps you to do a better feature engineering later on, and is not covered a lot by the courses because you need a lot of experience. There's not a unique way to do exploration data of the data. And you have to basically understand how the data is shaped, what's inside of the data set, and what is the meaning of each feature. And this is really, really important. And also you have to plot the features, the distribution of the features, and the correlation between features and between the target value that you have to predict. And we will see how and why later on when I will show you an example of the data EDA. This can be useful because you can find outliers. For example, if this is the target value, you have another. You plot it against another feature. You have a trend here. So the higher this feature, the higher the target. So you can draw a line here, and the model will basically do this. We'll try to find a line that models your data. But if you have an outlier here, this line will get mispredicted by a little bit. So will not be as accurate as we want to. So we will have to identify them and deal with them. And also missing values. Missing values can be encoded in very different ways. Usually, as we are seeing here, they are encoded as nans. NaN, not a number, but sometimes they are encoding as NA, or as 0, as -1, as -999. So it's not always easy to find missing values, but this is an example. If you plot the distribution, you see that all the values are between 0 and 1, except for some values which are -1s. Obviously, you have to check what's the meaning of the feature, but probably this is a missing value. It's a value that has not a real meaning inside the data set. This is an example for how important exploratory data analysis is. This is an example that has been shown by one of the best people on Kaggle, which is high ranked on a lot of competition. I don't know his name because it's Russian, so it's not very easy to remember. And the problem was that you have to predict if a promo, a discount, was used or not by a customer. So each row here is a promo, and you have the ID of the person, then you have other features, among which you have the amount, the number of promos that are being sent to the user, and the promos that has been already used by the user. Can you come up with a way in which we can exploit this shape, this data, without even training a classifier? Pay attention that here you have, for example, multiple promos for more than once for the same person. Okay? I mean, it's not easy because he's very good, so it's not really easy to come up with a way right away. But for example, if you take all the promos from that person and you order them according to the number of promos sent, okay? You have here that this person, it did not receive any promos, and so he never used any of them. But then after that, he received the promo, and he or she used it. So this promo he is referring here is obviously this promo that he received, the first one. So you can predict that this promo has been used. Okay? So the same here. Then after that he received another promo, but he didn't use it, so he predicts 0. So he could achieve 80% of accuracy without training a classifier, a big neural network, or stuff like that. So this is important on the fact that if you understand the data, you can achieve very good scores, and you wouldn't be able to do that even using the biggest or latest model that you know. So after the exploratory data analysis, you clean the data, which is remove a lot of parts of the data which are not useful or can make your model less powerful in terms of prediction. For example, features with constant value. In general, the more features you have, the more likely will be your model to overfit if these features are not really useful. So it will not behave, it will not have a very good performance. For example, a feature with constant value, I mean, if nothing changes, it's not useful for the model because it cannot understand what's the relationship between that feature and the one that you have to predict. Duplicated features, I mean, the amount of information is the same, so you can remove that feature. Or duplicated rows. I didn't talk about validation, but for the people who know what's a validation set, if you have a duplicated row, one in the training set, one in the validation set, you will overestimate your performances because the model would have already seen that house or that sample, so will obviously predict it well. So you don't understand if the model is good at predicting new houses, new samples that it has never seen. Outliers, as we've seen before, or features with too many missing values. Then, after feature preprocessing, after data cleaning, you have feature preprocessing, and this is important to know what kind of model you will use, because the preprocessing might depend on the model that you're using. And one of the most used that you almost always do with preprocessing is scaling, unless you have a kind of model that is a tree-based method, in which is not really important to do scaling. It is the reason of scaling is that if you have a feature, for example, from a house, which is the square feet of the whole house, maybe in the terms of thousands of them, like 2,000 feet or something like that, square feet. But if you have another feature, which is the number of people living inside the house, you have like 2, 3, 4. Then when the model will generate the error will come mostly from the square feet, because it's a bigger value. So probably you will have an error with a bigger scale. So the model will ignore the other feature. While if you scale all of them, they all have the same scale. So they will be considered all in equal way. There are multiple ways, maybe more than that. But for example, min-max scaler, you scale the values from 0 to 1 for each feature. Or standard scaling, you put the mean to 0 and the standard deviation to 1, and the robust scaler, which is known to be less sensitive to outliers. Another important preprocessing is that you have, for some features, you have categorical data. So you have labels, you don't have numerical data. I don't know what lot config is, but you have some strings that represent what's the label of that feature, but your models need numbers to learn. So there are multiple ways to encode categorical data into numerical ones, and the two most used, but there is many of them, and it depends also on how you want to approach and what are the pros and cons, is that the label encoder, which is just assigned a number for each type of each label, basically. So you have like inside of the zeros and second, and you have a 2 at the 0 and second, and so on. And another kind of encoding is the one-hot encoder, in which you generate a new feature, for each possible label of the feature. So in this case, we have 1, 2, 3 possible labels inside FR2 and corner. So you generate 3 features, and you put a 1 when the sample has that label. Here, for example, you have sample 3 has corner, so the feature log-thick corner is 1. They have pros and cons, this and all the other encoding. For example, the one-hot encoder, you generate a lot of features if you have a lot of labels. And if the features become more than the samples, it can get complicated, and the performance may decrease, for example. Then you also have the problem that most of the models that you use assume that the data you're using is normally distribution. It's a Gaussian, the typical bell curve that you see in black here. And so, for example, if you have this kind of data, the blue one, the data is skewed on the left, and the model is not using data with distributed as a Gaussian. But fortunately, some of the features are log Gaussian. So if you do the log of the distribution, you get a distribution which is close to a normal distribution. And we will apply also in the example. Then after feature preprocessing, you have feature generation, which is really important. Feature generation is what makes the difference in terms of performances in a competition, because everyone can use a standard library with model, neural networks, and very complex models. But if you don't have features which express as good as possible the relationship with the target variable, you will not have a very good performance. So some example of feature generation is that for the houses, we have a year as a feature, a year in which the house has been sold, and a year in which the house has been remodeling the last time. And this could be important to measure the price of the house. If the house has not been remodeled since 200 years, probably it will not have a very good, very high price. But apart from the house example, if you have an address, for example, you can extract the country, the state, the city in which the sample is referring to, which could be useful because maybe it can distinguish on the geographic data, and maybe the fact that the sample belongs to something in a specific country can help the prediction. For example, if you have a date, you can exploit the model to make it and capture the periodicity. So if you put, instead of the date, you put the number of in terms of weeks, of months, of season, of year, of minutes, hours. If something is useful, because it relies on some sort of periodicity, maybe the model will be able to capture and increase the performance. But it's an holiday. For buying products, is really important to have a feature for holidays. And some models are linear. So if you do the log or the square or a power of the feature, we'll be able to capture also non-linear relationships. This is also another example. If you have some features which measure the distance between 2 points, and you have the horizontal and vertical distance, then you can generate the direct distance between them, which could be useful. Or for example, for the price, if you're trying to predict if a product will be bought or not. For example, generating the fraction part of the whole price. You have 249, you generate a feature which has 0.49, could be helpful because the fraction can model the perception of the customer, because if it has 0.999, maybe it's more likely to buy that product instead of having a round number as a price. So feature generation is really important, and during the courses here at Politecnico you don't see much of feature generation, because even here you don't have a rule or a standard way to do feature generation. You have to understand the data and have a lot of practice in feature generation and have some intuition on what could be useful for the predictions or not. Then you have missing values. As I said, there are multiple ways in which the missing values can be encoded, but then you have to convert them in a numeric value, and a numeric value that don't screw up your data, basically. One possible approach is to, for each feature, create another feature that says true or false, whether if the related feature is a null or not. Like in this case, here you have the none, and then if you have a none here, you put true. In the other case, you put false. Or some people feel you can fill it with a number that is not from the distribution, like minus 999. Or the more used ones are to fill the values with the mean or median, or the mode, for example, the most frequent for if you have categorical data. If the number of missing values is not very large, it will not change much your distribution of the data. Then we come to the part of model building, which is useful only if you have done really well all the previous steps. And I will not go into details. We have a lot of courses here about them. But basically, you can divide them in 4 groups, like the nonlinear linear models, like the logistic regression, which is not for regression, weirdly, it's for classification, the linear regression, the support vector machine, and so on. And you have a lot of models for each category. But one important part of inside the challenge is stacking, because every model, especially if they're belonging to different groups, they can predict differently your data, and you can leverage it. If you predict if you train different models and then you average their prediction, they will have a performance which is not worse than the worst model that you use. And this is really useful because if you combine the prediction of multiple models, you are like using the best characteristics of all of them, and so it's very useful to stack and use at the same time models that are belonging to different categories that we're seeing before, so that you can leverage the differences in each of them and the pros and cons that they have. Then the last part is validation, and whoever has done machine learning or data mining or soft computing, you know about that. Is that, as I said, you have a training set and a test set, but you have to validate your model to see if it's predicting correctly or not. And some of the models have the parameters, which are actually called hyperparameters, that you have to tune a little bit to see to perform, to increase the prediction performance, and you have to know which are the best values for these hyperparameters. So you need a way to validate what's the performance of your model, and you don't have the target for the test set, because that will be you wouldn't be able to meet your prediction, would be obvious, and so you have to validate on another data set, which you have to take it from the training set. So you will have a less data to train, but then you will be able to see if your model is predicting well or not. And so what you usually do is that you take, for example, the 20% of the training set, and you train the model with multiple times with different parameters, and then you compute the error that you have in predicting the validation set, and based on in which case you had the lowest error, then you choose those parameters, or you have an estimate of what will be the error on the test set. After you select the best parameters, then you train on all the training set plus the validation set, because the more data you have, the better it is. So you have an estimate from this training about this error, but then don't waste the data and use both of them for the final prediction that you will publish on Kaggle, on the platform. Another type of validation, which is used a lot, is cross-validation, which is useful because in this way you're testing only on some parts of the data and training using the remaining ones. But with cross-validation, you slice your training set, for example, in this case, in 3 parts. You take the first 2 and you validate on the third one. You take the first and the third as training set and you validate on the second one. You take the first one as validation set and the second one and the third one as training set. So you get 3 validation errors, 3 scores, and then you average them. In this way, you have validated on the whole training set. So you have a more reliable, because maybe you had here an outlier or here, and so if you trained only on this, you would not have seen it, or something, or the opposite. In this way, you validate in all the spanning all the training set, but you don't use twice the same sample, because if you use twice the same sample for validation, your estimate will be biased, which will not be correct. And so after that, you have found the best parameters, or you have found the best model that you want to use. So you train on the training set plus validation set, and you predict the target from the test set. You have these will be samples, houses, but you don't have the target. So you predict and you upload it, do a submission on Kaggle, and your prediction will be evaluated based on how much is close to the real target. But the test set is divided more into public and private. With Kaggle, and I will show you, you have a leaderboard which is the ranking of all the groups, the teams with the relative score. And this leaderboard is public, everyone can see them during the whole time of the challenge. And is based on usually half the test set, which is the public part. And because then at the end of the competition, after 3-4 months, your prediction will be evaluated with on another part of the test set. This is because if you submit predictions which are kind of random, I mean, you can tweak some things and put random submission. Maybe after 3-4 months, you get by random chance one that is good. But then if you test it on the private, they will not be good because it's just done by random chance. It's not coming from a model which is able to generalize and predict samples from samples that has never seen before. So sometimes it happens that
Should we use the public test set as to extend our training data?
Not too much, because the problem is that when your model predicts very well to a data set but not to another set, it's called overfit. So if you use too much the validation set, you're basically doing what I was saying, that is your model, you will train the model that is the most able to predict the samples from the validation set from the public test set. I mean, if you use too much this as a way to decide which model to use, which parameters to use, then it will not be reliable enough, because you will have found the model that predicts best this one, not in general. So it should be a way to test how your model is going. But if you rely too much, then at the end of the challenge, maybe you're second, third in the competition, and on the private test set, on the private leaderboard that is published at the end, you are 35, 300, or something like that. It's important to find the model which generalizes the best, because otherwise, as it happens a lot, it happens, for example, for the recommender system course, because as a challenge, a lot of people were top and then fell down from like 20 positions because they were overfitting on the public leaderboard. So yeah, for the workflow point of view, that's it. If you have some questions. No? Okay, so I think we can start to work. So we'll show you first how the website Kaggle, the platform. So this, for example, is can you see? Yeah. This is the house prices competition. As you can see, it's ongoing, doesn't have an end, because it's always ongoing. And usually you have a description of the competition. The kind of measure that I use for the evaluation, this is important because you have to find them. You want to find the models that achieve the best scores, but you have different way to evaluate your model. And if you try to optimize on the same that you have, that they are using, you will have a better score. And in this case is the root mean square error, which is basically you take your prediction, the actual value that you don't have access to, you do the difference, then you square it, then you sum those squares for all the samples, and then you do the square root. And in this case is between the logarithm of the predicted value, the difference is between the logarithm of the predicted value and the logarithm of the observed one, which is really important, and we will see why later on. Then you have how your submission file will be structured. Then you have tutorials and a lot of information. And in the notebooks part, you have a lot of notebooks from people who work in the competition, and you can use that to learn. But I would suggest you at the beginning, especially because of I will show you, you will have some material. But then if you worked on the problem a long time, weeks, months, you don't know how to improve further your models, you can look at the notebooks, which have a lot of information, and also from people who ranked top in the leaderboard. And also there's a lot of people who is doing a lot of very good exploration data analysis, which could be very, very useful to understand how the data is done. Usually it's better to do it on your own at the beginning, because otherwise you will not understand the data enough. But then you can also look at the other ones, because it can give some insight that you were not expecting. And yeah, there is a forum with all the people that can ask questions. Then you have the leaderboard. So this is the public leaderboard, and you can see all the people with the relative score, the members, and how many submissions they have done. This is the public. Obviously, you can't see the private one because the competition has not ended. And for this kind of competition that never ends, you will never see the private leaderboard. But I mean, for learning, you can use this as a reference on how your model are going. Your rules and stuff like that. Then there is the description of the data, which is the first step for a good exploration data analysis, and we will use it during this example. So, for example, this is the data description, and you have for each feature what's the meaning of the feature. You don't always have that in all the competitions. Sometimes you have to explore the area of the subject of the challenge to understand what the feature really are. But in this case, they are all described, and also the all possible values are described. And this would be also very useful. For the notebooks, you can create your own notebook even if you don't publish them, because you can use Kaggle to compute and to train your models without using the resources, the CPUs from your computer. So if you're training something kind of heavy, you can use their servers basically. Sometimes you can also use a GPU for like high batch models, like neural networks or something like that. But you have a limit. Obviously, you can go forever, and after 9 hours, I don't know, it resets. So you cannot run a model very heavy that runs for 18 hours because it will get interrupted. And also about the GPU, you have a limit of how much you can use in a week. So I think we can start if you don't have questions. We have some time, so I will try to write. But then if it takes too much, I will use the code that I have already written. Okay. So these at the beginning are just libraries that I'm importing: NumPy, Pandas, Scikit-learn, the one that I was telling you about. And then here on the top right, can you see enough? Can you see on the back? Yeah? Okay. Here on the right, you have some like the versions of you can save the version of the code that you are using. And here you have the input data and the output data that you will use to obtain to get the submissions. So as I said, I will not go in the details. Oh yeah.
I see the icons on the right side there. Is it like collaborative with notebooks?
The notebook, I'm not sure. Could be, I think. Yeah. Also because I think they could be collaborative. I'm not sure about that because last time I worked in a competition, this tool was not here, was not developed yet. So I think it could be, yeah. But you can use Colab, for example, to work on the. There is a platform called Google Colab, which is basically this. So you can also use that one. The advantage of this is that you have the input already here, so you don't have to load it every time. and it's well integrated with Kaggle. So we have the training and the test set. So we can, if you write just train here, it will show you. Oh wait, I have to run the libraries. It will show you the data. So for the training set, we have 1,460 rows and 81 columns, in which there is also the ID, and then we have a bunch of other features. I would suggest you as an exploratory data analysis to understand what these features are, because it will be useful for the feature generation part. As we can see, there is already some features with a lot of missing values, and we will have to deal with them. And at the end, you have the sale price, which is the price that the value that you have to predict. And so let's start. I will start. I wanted to do first like a blind coding, in the sense that we are not. I will not do like exploratory data analysis and run like independently of the problem. I will impute. I will fill the missing values with mean, and I will scale without thinking about the features, and I will predict without understanding the data. And we'll see there is the performance that you get in this case, and then the other case in which we also exploit the features and understand them, there will be different scores. With the first one will be much lower than the first one, than the second one. And so first, let's extract on a different variable the target, the y that we have to predict, which is from train, is basically this column here. So even if you don't know NumPy, Pandas, all these libraries, I would like you to focus more on the concept than on the details of the code, because then after today I will publish this code, so you will have it, so that you don't have to write stuff while I'm doing, and maybe you can focus more on understanding. So we have extracted the columns sale price and saved on a different variable, and so we don't want to have the target variable in our data set. So we should drop both the sale price as a column from our data set, and also the ID, because the ID is not really important, because it's a different value for each house, is not related in any way to how much the price could be. So if we have less features, is better. So we drop the column axis. Axis mean that if it's 1 is the column, if it's 0 is the rows. So we drop the column, and we drop also the column of the ID for the test set. Obviously, in this case, we will not drop the sale price, because we don't have a sale price for the test set. So it will not be present as a column. And so if we do x dot shape, we can see what are the dimensions of the two data sets. So we have 1,460 rows and 79 columns, and around the same amount of rows and columns for the test set. If you write dot head, you can see the first rows of that data set, which is useful to not get really good big amount of rows to see. And so, as I said, blindly, without doing any exploratory data analysis, we will have to work on both the data set, the training set, and the test set at the same time. For example, filling the missing values. So it's useful. You could do like manually doing both the code for the training set and the test set, but it's more easy to save the number of samples that we have in the train set. So with shape, you take the first element of shape, so you get a number of samples, and you concatenate the training set and the test set. Sorry. So you will have almost double the number of rows. And then after we have done all our processing, we can split it again and use them separately. Okay, no error, good. So after that, we should see how many missing values we have for each feature. And there is a function from pandas called x is and a. So for each feature, we compute the number of samples that have a null value, and we sum them, and then we sort them based on how much they have in descending order, so that we see more the feature that has the most, and we plot the first 40, for example. So we see that we have like 2,009. How many are those? Around 2,900 samples, and almost all of them for these features are missing values, and we will have to deal with that. A possibility is to drop the feature if there are too many missing values, but we can see that there is a reason for why this value is so high. So another important part is that we have to treat differently numerical features and categorical features. So we want to find which ones are the numerical ones and which one are strings for categories. So we can check the types for each feature, and if it's not an object, it will be a number, so it's numerical, and we can use the categorical as just not the numerical. This tilde means not numerical, because if you show numerical here, you will see that for each feature you have true or false, and if you add this tilde here, it's just a not. So this will be false, it will be true, this will be false, and so on. So let's go back. After that, we can start filling the missing values. And for the numerical features, we will do the mean. We'll take for each feature the mean, and instead of the missing values, we will put that value. So this is through a class from scikit-learn, which is called simple imputer. And so we take all the columns that are numerical. You do it with this lock. The thing before the comma are the rows, and we will take all of them with a double dot. Then after the comma you have the columns, and so you select all the columns that are which are numerical. And usually all the scikit-learn classes, as most of them, the fit transform. Fit means compute the mean, in this case, based on the data, and transform is apply the transformation, so replace the missing values with the mean. So we take the same data. So the numerical data are transformed and saved as numerical data again. Let's see if it works. Yeah. Let's do the same with the simple imputer again for the categorical one, but in this case we will impute. For categorical, we cannot compute the mean. We will take the most frequent value. So the strategy is most frequent, and then you can do the same thing. You take the categorical ones, imputer, you fit transform, based always again on the categorical features. See if it works. Yes. Then we can see now how many null values we have, in the same way as we did before. Hopefully we will not have any of them, because we have all replaced them. Let's plot the first 10, for example. Yeah, So we sorted them from the biggest, and from the biggest we have 0. So none of them has missing values anymore. Then we have to encode the categorical variables as we saw before, and we will use the in this case it's called ordinal encoder, but it's basically the label encoder, which you have a number for each label of the categorical variable. So you have ordinal encoder, and in the same way as before, you have the fit transform function, ordinal encoder fit. In this case, fit means see what are the different values that that categorical feature have, and then transform is change that feature. Okay, no error so far. And so now we have worked on the whole data set, joined, trained, and test. Now we can split it again so that we can train our models on that data. So we had saved the number of training sample, and this is a slice. We can with pandas you can slice the data set in the same way you do with the list. So for example, we had 1,400 samples, so you take all the rows that are up to 1,400, and you also take the test set as all the samples from 1,400 and so on. Let's see, just to check if it's right, the shape of our dataset. Yeah, it's like before. We have 79 columns and for 1,460 rows. Then, last part before validation and prediction is the scaling that we said. We will use the robust scaler because, as I said, is less sensitive to outliers. And in this case, we want to normalize the features which are numerical, not the categorical ones, because the categorical have been encoded to numbers, and they don't need to be scaled. So we will have to first compute the categorical, the scaling for the numerical values. So we do fit transform again on the training set, only the numerical features. But then to obtain the training set, we have to concatenate them with the categorical one. This can be done with the horizontal stack from the NumPy library. So they are stacked on the horizontally. So the categorical ones. Then you have this and this, and you do the same with the test set. But in this case, best practice is to not do fit transform, but to do just transform. So you have fitted the scaler based on the features, based on the samples of the training set. So it computes the mean, the standard deviation in case of standard scaler and stuff like that, and then applies the transformation of the test set based on the training set, to try not to make our data set be influenced by the distributions also on the test set. Then if you have different distribution, it's another problem, and you have to deal with that in a different way. But so now we have a training set and a test set which are scaled. Technical thing is that this code returns a NumPy dataset, NumPy array, and if we want to keep these features, because if I show you now how it is like now, wait. Yeah. If I show you now, you don't have this data frame shape that you have before with the features with the name for the columns and something like that. But we can just solve this by saving the columns before transforming the data set. So we have calls equals to xtrain columns. This returns a list of the columns, and then xtrain would be a data frame from Panda. Yeah, as I said, don't focus too much on the code. You will have time to learn it and to learn how it works. But in this way, we create again a data frame back using the columns that were at the beginning, and we do the same with the test set. So if we now see what's the training shape now, you see back the columns and their characteristics. Now, time to predict. So we will use for example, now a linear regression, which is kind of simple, and it works fairly well. And also, sometimes you have 1,400 samples, which is not enough. Is not much. So using very complex models, sometimes it still not be useful because there is not much complexity to be captured from a very complex model. So we will do the cross validation that we have seen, that's dividing the training set in multiple folds and doing the test multiple times, and so that we can see what's the performance of our model. There is no scoring method implemented in this function for directly computing the root mean square error, but you can use the mean square error. Okay, and then you can compute the square for that. It's negative, so you will have to compute minus root. And then we do it for dividing the data set in 5 slices, 5 folds. So for each of the 5 folds, we take the mean. So we have mean scores, and we compute the mean from the scores, and we print the RMS root mean square error as I said, and the square root of minus mean scores. Let's see. Okay, so the prices are usually ranging between 100,000 and 400,000. As an average, kind of, we can interpret it in this way, error, we get 36,970,000, which is not really good, but we will try to improve it. And so let's be careful that in this moment we have not used the exact evaluation method that the platform is using, because in that case they were computing the log of our prediction and the log of the ground truth of the targets before doing the mean square error. But we will see that later on that we will change that. So we will fit them again. So we take the linear regression, we fit on the data so that it learns from the training set with the respective target. Then you predict it you predict the values, the targets for the test set, and then you save the results. Then here is done only to shape the output files so that it's matching with the submission format that they are asking. Say price. So we save for each sample of the test set the ID and the prediction that we have. we save it to a CSV, and we call it, I don't know, linear regression simple. Let's see if we have some errors. No. Okay. So now in the output we see this is here, this file. We download it. We go to the page. We submit. We submit our prediction, and we see how it goes. Okay. Oh yeah, I forgot, because I don't have to put index. What was that? Yeah. Index. Oops. Must be no index. Okay. Now should be updated. So let's upload again. Okay, it's uploaded. And we got as a score 0.17. This is different from ours because they use the log scale before doing the error. And let's see how we are placed in the leaderboard. Okay, out of AMA, I think, yeah, more than 5,000, we are 4,000, which is not really good. But we will do very briefly a better, if we do data exploration and we see how the features are structured and we modify them accordingly, we will have a better score. So since we don't have much time, I will use directly the code that I've used, that I've tried, that it works. So let's see, let me edit it so that I can use it, so that we save some time. Then, as I said, I will publish it so you can see the code and see better how I did most of the stuff, if it loads. Okay, so the backbone is the same as before, but in this case, for example, we run this, then we run this. These are the same as before. So we have the same data, but then, for example, before doing anything, we can check what's the correlation between all the features that we have with the training, the target that we want to predict, and we can see which features are the ones that are more correlated with the target, which can be useful because I think probably these features are the most important ones. So overall quality of the house is correlated with 80%, which is kind of obvious. The highest quality, the highest the price, or the size of the living area, or number of cars that can fit inside the garage and stuff like that. So when we will do exploratory analysis, we should focus more on that features. So I do exploratory analysis on a lot of features, but for example, for this one, I will show you only this one because it's one of the most interesting one. You see here that you have a trend. The highest the living area, the highest the price, because this is the target that we want to predict. And then you have these two guys here, which is obviously outliers. You have this trend, and then you have very low price for a very big house. So after that, we should remove these outliers because they will influence negatively our model. And so we remove them. We plot, just see which one are those, and are two, as we expected from here, and we drop them both from the training set, the samples from the training set, and the target that we want to predict. Then, as we were doing before, we concatenate training set and test set to use both of them at the same time. And here, you remember that we had this part with the data description. If you see from here, you have that MS subclass is 60, 20, 70, seems to be a numeric value. But if you look in the data description, it says that subclass identifies the type of dwelling involved in the sale. And so you can see that it's actually a categorical value. This 20, 120 is not a numerical value. So we can just make it here an object, so it becomes a categorical value because the value will be strings. As we did before, we look at how many missing values we have for each feature. In this case, pool QC, we had a lot of them. But if you look at the data description, pool QC, the missing value is not a missing value, it's not random. Has a purpose. It means that he has no pool, which is a characteristic of a house. It's not a value that has been wrongly put inside the data set. So we should consider them as labels of our data set. And there are a lot of features that have these characteristics, and I just listed them. And I will put, instead of the missing value, the string none as a new label for that feature. Then there is also the utilities. When I was inspecting the data set and I was looking at the counts of values, utilities had two values, all pub or new C way. I don't know what it is because I didn't do further analysis enough. But you can see that almost all of them are all pub, and one as another value. So this is basically a feature with constant value. And also the no CUA sample is inside the test set. So our model doesn't train on any sample having a no CUA value. So we drop this feature because it's not useful. As we did before, we distinguish in numerical and categorical. And now we have, again, now we can plot the number of features having the null values. It's different from before because we have already filled some missing values. Then we impute, as we did before, with the mean and the median and the mode for the categoricals. And now we should not have any features having a missing value. Ordinal encoder, as we did before. And also, if we look at some features like this lot area, we see which is not normally distributed, it's not a Gaussian. While we said that if we should try to use features as much as possible that have a Gaussian distribution. So we look at all the features and compute the skew value, how skewed is the distribution. And for the ones that have a very high skewness, we do the log transformation that we said before to try to unskew it as much as possible and obtains a normally distributed.
What is skew?
Skew is, if you see, I will show you the difference of before and after. If you see here, you see that the shape is really sharp on the left side, but then it decreases more slowly on the right side. In fact, there are still values here. So it's not symmetrical, the distribution. But if you take the log, you get this. This is the distribution after applying the log to the values. And you see that it's more like a bell curve, typical of the normal distribution. And the two, they're called tails, they have roughly the same size. So now it's more normally distributed and will be better for our model. Okay?
Mathematically, what is it? From a mathematical point of
How is
view?
it computed?
No, I mean, how how do you calculate skewness?
From how the distribution is symmetric. So if you, for example, if you get the mean on the highest value, what's the range on the left side and what's the range on the right side? And okay, so we have preprocessed some features. We could do, I just tried a random example of feature generation. We have the square feet of the basement, square feet of the first floor, and square feet of the second floor. Could be useful to have a total area, total amount of square feet of the entire house. So we can generate a new feature by summing them. Then we have generated new feature, so we should recompute which are the numerical ones and the categorical ones. As we did before, we can now split again the test set, the training and test set. We have two sample less with respect to before because we had the outliers that we have removed. We scaled again as we did before. Now, if you see, I will add this distribution plot of the target. Also in this case it's not symmetrical. You have a wide range on this side and a small range on that side. So we should take the log of this. Also suggested by the evaluation metric that they were using. They were using the log of your predictions with the log of the target variable. So we can take the log of the training set, and you can see again how is it shaped now. Yeah, it's more unskewed, more balanced. And then we compute again the linear regression. In this case, our value is more similar to what we have seen before, because now we're using the log of the training set. So we have a root mean square error, which is more similar to the one that we have seen in the scoring from the platform. As we can see from our cross-validation, it looks that it's going better than we did because before we had 0.17, if I remember correctly, and now after all the changes that we've done, seems that it's 0.12 basically. It's not always very reliable because you can not have enough data to estimate your error, or for the distribution may be different from training and test set, but it gives you an idea. So we predict again. So let's see how it goes for now. Okay. Okay. Yeah, sometimes it takes time to compute the score because their server are kind of busy. But while it computes, we can finish, because now I use only linear regression. Then another possibility is to do the stacking that I was mentioning before, using multiple models and arrange the predictions. And for example, there is this XGBoost regressor, which is used a lot because it's very powerful. It's not it can use also a data set that contains missing values, so you don't have to fill them, and also can exploit the fact that they have missing values to extract useful information. But it's a little heavier. It has a lot of parameters, so the parameter tuning, finding the best parameter using cross-validation, for example, would be harder, and it's more likely to overfit because you find the specific parameters that are good in predicting your kind of subset of the data. Wait, what is happening? Okay. And so, okay, I don't know why. And so it's powerful, but for very simple data set is not overblown, is not very, doesn't make so much of a difference. In this case we have 1000 sample, which is not really enough. So no, still not done. So we will compute, we will see what's the cross-validation error using XGBoost. XGBoost is doing for all 5 the folds of the cross-validation. So 0.116, so it's not that different from the 0.119. Basically because our model, our data is not very big and not very complex, so using a very powerful model is not that different with respect to linear regression. But we will see that by stacking both of them, so you can use this voting regression, which does basically an average of the predictions. You put the your linear regressor and the XGBoost, and you compute the cross-validation error. And you will see when it finished, you will see, yeah, the last one. You will see that the performance are better than both of them. So using both the model at the same times, yeah, 0.112 instead of 0.116 and 119, because using both of them, they maybe were able to predict better some parts of the data one and some parts of the data the other. So combining them gave a better result, and so we save this prediction because we see now still going. So, okay, with the using exploratory data analysis and all the changes, the log that we've done, we arrived at 0.212 when before we had 0.17, and let's see where we are placed in the leaderboard. 1,400, starting for 4,000 in I don't know 20 minutes. With the exploratory data analysis, we have climbed 3,000 positions. Let's now see with the other. Okay, now I should see. Yeah, with the ensemble method, the stacked method with more than one. Now from this part will be, the more you go obviously up in the leaderboard, the harder it is to improve your score. So every time you get close to the top, it's always harder, and it's improved way a little more. So let's see now. We went over 1,000. So in an hour, what was that? We arrived at 1,000. There is a lot that you can do more. For example, you can impute better the missing values. There are ways to, for example, do a prediction of the missing values based on the rest of the data using a regressor, or you can find more outliers and remove them, training more models and training them better, finding the best hyperparameters and stacking more models, and from time after time you will go up and up on the leaderboard a little bit. And so then if you are stacked, you can see on the notebooks or in the discussion if there are useful insights for improved more. So I think for the groups, for the Kaggle competition groups, if you are completely new, I suggest you to start with the Titanic dataset, which is even a little bit simpler than these ones. It's a classification instead of a regression. You don't have much samples, and so that since at the beginning you will have some problems with the libraries, the code, and stuff like that, you will not struggle too much with the data, but just with the code. If you have some experience or you want to try, you can try to replicate these house prices as I did now and try to improve the model. But I I suggest you to work to try give it a try, because it's interesting, and these kind of projects, they simulate what partially simulate what you will do in a real machine learning project, and it will be helpful also if you want to do the master here or in a lot of other universities, because they have courses like data mining, or like I think they're doing it for artificial neural network or for recommender system, in which part of the evaluation is based on a challenge similar as this one. So if you start doing that, if you start to get your hands dirty, even before you have learned the lot of theory that you will learn during the master, will be still very, very helpful, and will help you a lot. So I don't know how we can arrange the groups, if now or in the Telegram group, so that everyone can join based on their experience and their preferences. And yeah, I think that's all. If you have some questions. No? Okay.
The last thing you did with the averaging the model results, why do they sum the strengths instead of summing the weaknesses?
Because if you average,
do they give a confidence on the prediction?
Not. I mean, you can use you can do it like weighted average of the predictions, and you can train your weights that you give to each prediction based on your cross-validation score. So it's more parameters that you can use for tuning.
Mm-hmm.
So in that case, you can choose, you get directly towards combining the strengths instead of the weaknesses, because you're tuning on that parameters. So in this case it worked. So of you, who would like to form? I mean, from how I want to set this kind of meetings, it's not like that. I don't want to give lectures every 1 or 2 weeks. But for how I would like to do it is that you work either by yourself, but it's more interesting and useful to work in groups. Either during the meetings or at home, and then during the meetings, if you have any problem, we can talk about it together, or doing brainstorm if you're working on the same competition from different groups to try to improve the model or the code in general. And yeah, if you have any problem, we can talk about it all together. So that's it for me. So if you want to, I think since a lot of people have to go away, we can arrange the groups on the Telegram group. Also, I think some of you already know each other, so you can obviously start with groups from people you know. And yeah, thank you very much for coming.
Thank you.